Well, moles made some things easy, but this is going to be a little more difficult. However, this is a lot more practical for what you actually might be doing in life if you do a lot of chemistry. So be able to define percent composition. That's the percent by mass of an element in a compound. An empirical formula, which I will get to at the end of the lecture. Be able to determine the percent composition of a compound if given the compound's formula. Be able to determine the percent composition of a compound if giving the one element's mass in that. And be able to calculate the empirical formula of a compound and compare between empirical and molecular formulas. That last one's a really easy exam question, and that first one that's not the definitions is a good amount of math. So let's say that Greg mines 120 kilograms of hematite, which is a type of ore containing iron. He wants to extract the iron using one of these furnaces. How much iron can he get? In order to know that, you have to know the percent composition of iron in hematite. And the percent composition is a percent by mass of each element in a compound. So let's look at an example here. This is the book's example. If you have 13.6 grams of magnesium oxide, and what you do is decompose it, which is basically removing the oxygen, and you get 5.4 grams of oxygen produced. So what was the percent composition? So percent of magnesium is the mass of magnesium divided by the total mass. Percent of oxygen is the mass of oxygen divided by the total mass. So 5.4 grams divided by 13.6 grams times 100%, because it's a percentage thing, gives you oxygen is 39.7%. Whereas the percentage of magnesium is 100%, well, minus 39.7, because everything has to equal 100%, and that's going to mean that the percent composition of magnesium is 60.3%. So what about that hematite? Well, that's iron 3 oxide, so it's got your chemical formula using that crisscross method of Fe2O3. For each mole of this, which is not going to be relevant to his grams, but is going to be relevant to our example here, there are 2 iron and 3 oxygen. So if we were to calculate for like per mole example, it'd be 2 times the molar mass of iron plus 3 times the molar mass of oxygen. So a mole of this is going to be 159.7 grams. So that's not percent composition. If you want to know percent by mass iron, it'd be 111.7 divided by your molar mass, and that means in a mole you're going to get 69.9% iron by mass. If you wanted to know the mass of oxygen, it's all 30.1% oxygen by mass. And that can kind of help you a little bit. You've got 120 kilograms of hematite. How much iron is this? Well, you know from previously, it's 69.9% iron by mass using that molar ratio. If you take 120, which is the number of kilograms, it's actually a real lot of kilograms of hematite, and you multiply that by this percentage, you're going to get 83.88 kilograms of iron out of that. It's good harvest there. You can use percent composition as a conversion factor to determine the amount of an element in any amount of compounds. So that means no matter how much popcorn you're going to burn, you can actually determine how much carbon you'd get out of that. Carbohydrates are generally CN times H2O to the N. So percent carbon in one of these is about 40%. If you remove the water from anything, which is how you burn it without really making it smoky, it's kind of tricky. You really have to be skilled at burning your popcorn. You get 40% carbon from anything that is going to contain carbohydrates. I actually do this in a lab experiment once, and it ended wrong with me. I caught on fire. An empirical formula, here we go. It's the lowest whole number ratio of atoms or moles in a compound. Now, this is different from the molecular formula. The molecular formula is the actual ratio of atoms in a molecule. This is for determining percent compositions. Are going to actually give you empirical formulas. Percent composition don't tell you how many atoms there are in a molecule. They just tell you the empirical formula. So we see some examples of carbohydrates. Most carbohydrates end up having the same or very similar empirical formulas because of the way that they're made of polymers out of the glucose monomer. So let's calculate an example here from the book. You have something that's 25.9% nitrogen and 74.1% oxygen. What's the empirical formula? So first you're going to convert that to moles. You get 25.9 grams of nitrogen. If you think 1 mole of nitrogen is 14.0 grams, that's 1.85 moles of nitrogen. And 74.1 grams of oxygen, you convert that to moles, is 4.63 moles of oxygen. So the ratio is 1.85 to 4.63. Those need to be whole numbers though. In order to find that out, you divide each by the smaller number. So divide them both by 1.85, and you get 1 to 2.5. Again, not whole numbers. So you have to multiply that until you do get whole numbers. And you can see this is a fair amount of math. So you end up getting N2O5 as your empirical formula because you have to have whole numbers of elements in a molecule. Now that's molecular versus empirical formulas. The empirical formula is that simplest whole number ratio of elements, and the molecular is what's actually happening in the molecule. So, like NO2, okay, that's your empirical formula. But let's say that was actually dinitrogen tetroxide. Well, that's not going to be NO2, clear, it's going to be N2O4. And they can have several different molecules with the same empirical formula. I like your book's example here. It gives the example of acetylene, which is C2H2, and styrene, which is C8H8. One of those is going to be used for welding, and the other is going to be used to make styrofoam containers. But they both have the same empirical formula, just by having different molecular formulas. Now, hydrates are something I just wanted to touch on here. Take a little extra time to explain. You're going to see these pretty often, where you have something like barium chloride, and it's being sold as barium chloride dihydrate. Now, what happens here is you get the ionic compound, barium chloride here, but you also have water involved in that. And that's because the ionic compounds may form crystalline structures with water. Keeping barium chloride on its own means it will eventually find the water, and it will basically absorb that water from the air and become that hydrate anyway. So storing it as a hydrate is just a more stable way of doing this. And we're going to see these in our lab quite often because we have a lot of hydrates in our lab. So in measuring molar formulas, you have to take into mind the hydrates.